In section 7.4, we're going to talk about a very specific and narrow concept of when we can find the sum of infinite geometric series. So, as I mentioned when we were talking about infinite series, we can't find the sum of an infinite arithmetic series. It is not possible. Under some specific circumstances, we can find the sum of infinite geometric series. And so we're going to talk about under what circumstances can we, under what circumstances can't we. And part of what we're going to look at is this idea of partial sums, because it's a guide to when you can and when you can't. So the idea is if we do a partial sum, doing partial sums might be taking and doing so this idea of doing partial sums would be taking and viewing what's happening as I do a sub 1 plus a sub 2, it will equal something. And then if I do a sub 1 plus a sub 2 plus a sub 3, it will equal something. So by finding adding one more term each time, this allows me to examine these partial sums for the trend in what's happening to the sum of the series as we're moving forward. And so let's do a little practice on that so you can get the sense of why we're doing this and why this is important. The type of problem we would use in terms of an infinite geometric series and finding sums is an idea like this, where a pendulum is set to swing freely. And you know, with a pendulum, each time it swings back, it swings just a little bit less, a little bit less, a little bit less, and eventually it's going to stop. So this is the type of circumstance where we could find that sum. And as we go through and learn how we find the sum of infinite geometric series, then we'll return to this problem and find out how do we find out the total distance that the pendulum has swung as it keeps going back and forth and back and forth and back and forth until gravity eventually stops it. So if we look at the idea of the partial sum, so if I just look at these two, 1/4 plus 5/4 is going to be 3/2, 6/4. If I look at three of them, then I'll have 5, 6, 31/4. So this went from 1.5 to almost 8. Right? And if you look at this one, if we take the 31 plus 125, then that's 156/4. Right? And if we add that to 625, then we're going to have we're going to have 781/4. So you can see how with each new term that I add, my growth is becoming greater and greater and greater. And what this is this is an exponential growth function. So this is what it looks like when you have growth. Okay, now if we take a look at this guy, if we do 1/2 plus 1/6, so that's 3/6 plus 1/6 is 4/6, or that could be looked at as 2/3, right? If we go ahead and we take the 4/6 and add 1/18, that's going to be 12/18 plus 1/18, that's 13/18. And then if we add that to 1/54, that's going to be 39/40/54. So when you take a look at this, if I simplify this out, right, that's 20/27. So when you look at here, we're at 2/3, and the amount that we have changed is very minimal, very minimal. So what you're finding is that in this case, with each successive term, I had a greater and greater change to my partial sum. But with this one, each successive term, they're getting smaller and smaller and smaller, so I have less and less impact to my partial sum. And this is what it looks like when you have a decay function. And the important thing to remember is that in the circumstance where we have decay, with each new successive term in my series, it comes closer, the value of that term comes closer and closer and closer to 0. So the more and more terms that I add, the less it impacts the actual total. So this is the circumstance where we can actually find the sum of an infinite series because each new term doesn't impact the sum very much. So go ahead and practice finding partial sums. Go ahead and do problems 4 and 5, and then come on back to the lecture. Now we have a formula, and it's a very simple formula actually. So if you compare this to the sum of a geometric series, this is much easier to use. All I have to do is take the first term and divide it by 1 minus the common ratio. So this is a really easy term, but what you have to remember is this other data here, that the absolute value of the ratio has to be less than 1. And if you remember, that's also how we would find that it was a decay function when we studied exponential functions. So this is an exponential function, but it's exponential decay. Okay, so you can see here my common ratio is 1/5. Yes, I can do that. Here it's negative 1/4. Its absolute value, though, would be 1/4. Yes, I can do that. The absolute value of negative 3/7. Yes, I can do that one too. But if you take a look at this one, 4, I can't do that. So just in looking at the 4 problems I've laid out here, this one, I can tell you now, is not possible because my common ratio is greater than 1. The absolute value of my common ratio is greater than 1. Okay, now on these other terms, this is a special case because you see it's not in the correct form. So I may not be able to find a sub 1 immediately in this case. But I can do the others there, vanilla, they fit right into this. So I'm going to take my first term, that's 8, and I'm going to divide it by 1 minus the common ratio, which is 1/5. So I'm going to have 8 divided by 4/5. That means I'm going to multiply it times 5/4. 4 goes into 8 twice. 2 times 5 is 10. So the sum of this infinite series is 10. Okay, in this particular case, if I take my first term, negative 2, divided by 1 minus negative 1/4, that's going to be negative 2 divided by 5/4. So that's negative 2 times 4/5. So that will become negative 8/5 is the sum of this infinite series. Now with this one, again, it's tricky. First off, I'm not going from 1 to infinity. I'm going from 0 to infinity. So I have an extra term. And right now it looks like my first term is 1. But what I need to do is I need to plug 1 in for this. So when I is equal to 1, so if I find a sub 1, that will be equal to negative 3/7 to the first power. So my actual rule here is going to be negative 3/7 times negative 3/7 to the n minus 1 power. Once I know the formula now, I can see that a sub 1 is negative 3/7. And I'm going to do 1 minus negative 3/7. So this is 7/7 and 3/7. So I'll have negative 3/7 divided by 10/7. Again, I'm going to invert and multiply. So the 7s will cancel, I'll get negative 3/10 as the sum. But again, this is the sum from 1 to infinity. I now have to take the 0 term, right? And I need to add it to this. So it's negative 3/10 plus a sub 0. So a sub 0 would be equal to negative 3/7 to the 0 power. Okay, and that would be 1. So this is going to end up equaling 7/10. So go ahead and practice that a little bit, finding these sums. Do problems 12, 13, and 14, and then come on back and we can look at something else. So one of the things we can do with this concept is we can take a look at how do you take a repeating decimal and convert it into a fraction. Because what repeating decimals end up being is they end up being this sort of a decay function. But what you have to look at is how much of the item repeats. So you see I just have one digit that repeats. So if we take a look at this particular item, I could write this repeating decimal as I could write it as an infinite series. It goes on forever. We know it goes to infinity. And I know that the first term was 2 times 0.1. And the second term is 2 times 0.1 squared. And the third item is 2 times 0.1 cubed, and it's going to go on forever. Okay, so what I know is that this item then is going to be 2 times 0.1 to the n power. So what I can figure out through all this is that my first term, a sub 1, is equal to 0.2, and my common ratio is equal to 0.1. So I can say that this sum of the infinite series is going to be equal to a sub 1, 0.2, over 1 minus 0.1. So this equals 0.2 over 0.9, which is 2/9. Okay, so I've taken my repeating decimal and I've turned it into a fraction. So if you take a look at this guy, you see that, oh, it's 130 that repeats. Right? So I know that this is going to be 130 times 1 plus 130 times 0.001 plus 130 times 0.001 squared. Okay, so another way to look at this is I could say that this is 0.001 to the 0 power. Okay, so when you start taking a look at this, I'm going to go ahead and work on just this portion of it. So because I know it's going to be a mixed number, right? So I know that my first term is 0.130, and it's going to be 1 minus 0.001. So I get 0.130 over 0.999. So that's 130 over 999. And then I take this part of it and make a mixed number. It's 130 and 130 999ths. And so that's how to go ahead and do this work. The important part is you'll notice how many decimals are repeating. That matches how many decimals I have here. I had 3 decimals repeating. I used 0.001, a number with 3 decimals. Here I had 1 decimal repeating, and I used 1 decimal for my common ratio. Okay, so go ahead and practice that. Do problems 25, 26, 27, and then come back and we'll finish up this lesson. So as my pendulum swings, it travels 18 inches on the first swing, so I know a sub 1 is equal to 18 inches. Okay, so that's important. On the first swing, that's going to be my a sub 1. And on each successive swing, it's going to travel 80% of the distance. So I know that this function, my common ratio, is going to be 0.8, 80%. to the n minus 1. So I'm going to have 18, this is my rule, a sub n would be equal to 18 times 0.8 to the n minus 1. So my first term, 1 minus 1, would be 0. 0.8 to the 0 power is 1 times 18, that gives me a sub 1. So if I want to calculate the total distance it has swung as it keeps going back and forth and back and forth and back and forth, that's going to be a sub 1 divided by 1 minus 0.8. That's going to be 18 divided by 0.2. And that's going to be 180 over 2, which is 90. Okay, so what I did there is I moved the decimal place, 1 decimal place in each case, and got it to be 180 over 2. The total distance ends up being 90. And that's 7.4.